Good morning again. Welcome back to the second segment of the opening session that is dedicated towards the top 500, Green 500, and HPCG lists and awards. This is a special year in a sense that the top 500 is celebrating its 25th anniversary. We will recognize this with a panel discussion in the second half of the morning. But before this, we'll come to the time-honored tradition at the ISC conference to talk about the lists and the awards. Here are my colleagues that will join me on the stage in a little while: Jack Dongara, Eric Strohmeyer, Martin Moyer, Wu Feng, and Mike Haru, who have all contributed in various roles to the top 500, Green 500, and HPCG awards. So I will jump right in because we're running this on a very tight schedule, and my colleagues and I are very proud to announce that, and for those of you who've watched news releases and everything else, it won't come as a surprise, but anyway, we will proudly announce that there is going to be a new #1 list, the Summit system, an IBM Power system that is installed at the Oak Ridge National Lab in Oak Ridge, Tennessee. This is the new #1 on the top 500 list, so congratulations to my colleagues. So I'm welcoming Buddy Bland and Jeff Nichols from Oak Ridge, David Turk from IBM, Ian Buck from NVIDIA, and Gilad Shiner from Mellanox. Congratulations. Congrats, Jeff. Buddy, congratulations. Congratulations. Hey, Dave. Congratulations. So let me pass on the certificate, one to the Oak Ridge team and one to David Turek for the vendors. And I'd like to ask Jeff to say a few words. We only let the #1 speak. And you're the #1, Jeff.
Thank you very much. Today we're announcing Summit as the world's most powerful supercomputer as measured by #1 on the top 500. We also are indicating that Summit is going to be the world's smartest supercomputer, and because it can actually calculate 3 quintillion calculations per second at half precision. So indeed, Summit is the world's most powerful supercomputer as the world's most smartest supercomputer. I want to thank the Department of Energy, the Office of Science, and the Advanced Scientific Computing Research Programs for sponsoring Summit and building Summit with us, and Barb Helland in particular, our sponsor. We couldn't do it without a team, and the team that you see up here represented IBM, NVIDIA, Mellanox, and Red Hat. With a team like this, we hope to stay at the top for many years to come. I'd also like to thank our staff who has been working diligently 24/7 over the past 9 months to actually put this system together and to be able to run something as difficult as HPL for the period of time that it ran. So thank you very much, and we hope to be here again in many years to come. Thank you.
Thank you, Jeff. One more photo up. All right, now a little specialty is that I would like to ask the team to stay here on stage, because in order to optimize, and we always optimize bandwidth and memory access, so you all come up here only once, because you also won the HPCG #1 award, and I would like to ask Mike Haru to join me here and make the announcement and hand out the certificate.
Well, I think it's been announced already, but congratulations to this same team for winning the HPCG award. Very proud of the efforts that you have put into that. Thank you.
Gracias. Okay, Mike, please stand with the group for a picture. Okay, thank you. I'm really proud to show a real-time implementation of a caching algorithm to get all those people on the stage only once and cut out 2 minutes from the performance here. So with that, now I wasted the time already, and I would like to ask my good old friend and dear colleague, Jack Dongara, to come and talk about number 2.
Thank you very much, Horst. It's my pleasure to announce the number 2 in the top 500 list, and that award goes to the Tahoe Light supercomputer. Tahoe Light was number 1 for four issues of the top 500. It achieved 93 petaflops, which is an impressive 74% of the theoretical peak performance for that particular machine. So I'd like to ask the people from Wuxi, Jin Gang and also Zhenxi Yang, to come up and accept the award for the number 2 this issue.
Yes, and the top 500 proudly announced for number 3, and my colleague Eric Strohmeyer will present.
So we also have a new number 3 system, and it is in the US as well. It's installed at our sister lab, Lawrence Livermore National Lab, the Sierra system, also an IBM Power 9 based system with NVIDIA GPUs, very similar to the number 1, but not quite the same. And I ask David Turek again from IBM and Bronislaw Sapinski to come up.
Okay, all photos have been taken. Thank you very much. We'll move on. Applause one more time. So we've on to Martin Moyer, who will present the number 1 in Europe.
Yeah, I'm pleased to announce the number 1 system in Europe. This is not a new system. Pete Stein, operated at the CSCS in Lugano in Switzerland, has been holding the top spot in Europe now for the 10th time in a row, which is a great achievement. Pete Stein is a Cray XC50 system and achieved 19.59 petaflops best impact performance. Yeah, ladies and gentlemen, please join me in congratulating Michele De Lorenzi from CSCS and Pascal Barbalosi from Cray.
Okay, and now let's move on to the Green 500, and I would like to ask our colleague Wu Feng to be on stage. And in order to celebrate the Green 500, he has even bandaged his broken wrist in green. So special applause to Wu for having this spirit here of Green 500.
Thank you. So yeah, in preparation for the Green 500 unveiling for number 1, this was done specially for this occasion. So I'd like to announce that this year's edition of the Green 500, the number 1, is given to the Shobu system. It's a PEZI computing exascalar zetascalar 2.2 system. It is a repeat number 1 from the previous list. The gigaflop per watt rating increased marginally from 17 gigaflops per watt to 18 0.4 gigaflops per watt through a number of innovations that you can hear a little bit more about at the Green 500 BOF tomorrow. So with that, I'd like to have Sunao Tori from Exascaler Incorporated to come up to accept the certificate. Thank you.
Thank you. Thank you and congratulations to all the winners. And I would like to ask my colleague and friend Eric Strohmeyer to come up to the podium and present the details about the top 500 list, the 51st list since 1992.
Thank you, Horst. So it is my pleasure and my honor to present some of the highlights of the new top 500 list, like I have done a few times in the past. Of course, it's been 25 years since we started the list, so it's a special date, at least for us. And luckily, there is actually some news to talk about. Here is a brief list of some of the topics I want to touch, each just a couple of minutes, because we don't have that much time. There is a new number 1, as you just heard about it, and I'm going to briefly talk about that, about the Summit system. There is actually pretty much a new top 5. Only one of the top 5 system has been on the list previously. 3 are new, and 1 is substantially upgraded. I'm going to touch the topic again, which I did in the past, about the slowdown of the growth of performance together with the aging of our systems, as well as the concentration on the top of the list. And I think that all 3 of those are actually related and tie nicely together. So I'm going to touch those. I'm going to reflect very quickly on 25 years of systems and sites. The Chinese story has been in the news for a while, and there's a new twist to that. I'm going to come to that. And one of the topics which we mentioned in the past a couple of times was industrial adoption of GPU accelerators, and there is news about that as well, so I'm going to talk about that. And then last but not least, the HPCG benchmark and the petaflops area in the HPCG benchmark, which just started. So we have a new number 1 system, the Summit system at Oak Ridge National Labs. It's the first system above 100 petaflops, 122 petaflops, quite impressive system. It is based on the Power 9 chip with 22 cores, just over 3 gigahertz frequency, and it is using a dual-rail InfiniBand, Mellanox InfiniBand, together with the NVIDIA Volta GV100 accelerators. Six accelerators for 2 processors per node, and over 4,000 nodes for a total of over 2.2 million cores. The other impressive number about that system is actually at the very rightmost corner, which is the 8.8. That is the number of megawatts averaged over the Olympic run the system achieved. Oak Ridge actually went out and beyond what we require for power measurement. They did a very high fidelity power measurement, the level 3 we call it, and they averaged the energy over the actual run. That helped them to achieve this number. The peak consumption during the run is higher than 8.8, but the average is 8.8. And that puts them in the top 10 of the Green 500 overall. I think they're actually number 5 in the Green 500 as well. And that's quite impressive for a system of that scale. So about the architecture, just a few highlights. As I already said, peak performance is actually over 200, and that is peak performance for 64-bit floating point operations. The 200 petaflops is a combination of the Power 9 as well as the NVIDIA Volta together. And if you know the Volta architecture a little bit, you know that the Volta can double its peak performance if you go to singular precision, 32-bit, and you actually gain a factor of 16 compared to 64-bit floating point operation if you go to 16-bit floating point operation. That is basically while this system has a peak performance of over 3 exaflops if you go to half precision and do machine learning on this system. So in that sense, you might have seen some articles, some press releases, that this is the first exaflop system and the first exaflop application has been run on it. And that is based on the fact that you can run on half precision and that you get a big boost based on the Volta chips in terms of peak and sustained performance. Each node has 2 of those 22-core Power 9 chips on it, and 6 of the NVIDIA Tesla system, NVIDIA Tesla chips, 608 gigabyte of fast memory, and it also has a non-volatile memory, which I think is also first in the top 10. Over 4,000 nodes, 4,608 nodes, dual rail Mellanox, and a nice file system to go with. Okay. So that's the number 1. The other yellow systems in the top 10 are also new or improved. The number 2 system, of course, is the previous number 1, the TOP Lite. It hasn't changed. The number 3 system, Sierra system, is the sister system to Summit. It's installed in Livermore. They received an award too. It looks like the same architecture, but they actually use only 4 of the NVIDIA Volta per node instead of 6. So there are slight differences. But again, they achieved a very nice Limpec performance of 71 petaflops. They didn't get around to measure or give us their measurement for the power number yet. That's the only one we're missing in the top 10 right now in terms of power consumption. Tianhe 2A or Milky Way 2A is an upgrade to the previous Tianhe 2, which had been on the list for, I believe, like 4 or 5 years. Has been the number 1 for quite a while. And what they did there is mostly remove the Intel Xeon Phi, which they used as an accelerator, and replaced it with an accelerator, a proprietary accelerator, the Matrix 2000. That allowed them to overall roughly double the performance they achieved to about 61 petaflops on the Limpec benchmark. But it wasn't enough this time around to stay in the number 3. So number 4 for Tianhe 2A. And the number 5 system from Fujitsu installed in Japan is also a new system. It's a Fujitsu-based system, Fujitsu Brahmachi server, and it's using the Xeon Gold 20-core processor together again with, I believe, dual rail InfiniBand EDR and the NVIDIA Volta chip as well. So Volta certainly has made an entry in the top 10 or in the top 500 in general. These are some of the systems. The lower systems, which are all in white, are the systems we had on the list before. They just moved a couple of positions down. So it's nice to have 4 new systems in the top 10 to actually have something to talk about, because the last couple of years I always told you not much is changing and things have slowed down. So one way to look at that and to show that things are still slow and we haven't sped up miraculously across the list is just look at the average age of a system in the list. So here I basically I say a system which came in now is brand new, a system which came in November is 6-month-old, a year ago is 12-month-old. And if we do that, we see for the first 20 years or so of the top 500, the average age of a system was about 7 to 8 months, less than a year. And that has, since about 2012, that has changed. And we have actually doubled the age of the systems in the top 500. And that has not changed this time around. So our systems are about a factor of 2 older than they used to be. We keep them twice as long. And the question is why? And I think there is one of the reasons for that is, and there is another effect which started around the same time. As I said, around 2012 is when the aging of our system started. If we look at a measure how concentrated performance is in the top 500 towards the top of the list, one way to look at that is simply look at the number of systems you need to accumulate half of the total 500 systems. And if you do that, we see up to about 2011, that number was between 40 up to 80. And since 2011, it has become much smaller. At some point, it was below 20. Now we are back around 35, 30 system. So there is definitely, at the same time as we have seen an aging of our system, a concentration towards bigger systems in the list. We seem to be spending more money on the very big systems, and they're overall relative to the list in general, to the average system, they grow in size. Of course, there's another effect which ties in with those two together, and we have talked about that in the past a couple of times, and that is easiest seen if you just look at the development of performance. That's our traditional slide where you see the sum of all 500 systems, the number 1 and the number 500, and we have seen in those curves inflection points at the bottom of the list around 2008, at the top of the list around 2013, and the rate at which performance has grown has dramatically decreased in the list. And towards the top, that inflection point coincides with the other two observations I just made, with the increasing size of system and with the aging of the system. So to look at this in a little more detail in a different way, I really calculated the year-by-year increase in performance we have seen on average in the list. That's the blue list. And I broke the trend up around 2013 again, that inflection point. And the upper orange bar is the average we had seen before that inflection point in the top 500. And the lower orange bar on the right of the graph is the growth of performance we have seen since that inflection point. Those two orange lines are at very different levels. It's highly significant. And in between is Moore's law as a red line. So to illustrate what that means, how much we have actually slowed down in terms of performance increase, I calculated out how long would it take to achieve 1,000 times improvement in performance. And 1,000 times, that's, okay, we go from beta to X. So how long would that take? If you take Moore's law, it takes around 15 years. So if you just rely on Moore's law, it would take 15 years to get 1,000 times X in performance. What we have seen traditionally in the first 20 years of the top 500 was that it took about 11 years to achieve that 1,000x. So it was substantially faster. It was a very nice thing. But now we are at that lower orange curve, and that lower orange curve actually translates to about 20 and a half years, almost twice as long, to achieve the same increase in performance. And now I'm just tying those three things together. It takes twice as long for us to achieve a certain increase in performance than it did before. And because there doesn't seem to be another big incentive to buy new systems, we wait twice as long to buy a new system. But because we were able to save more money during that time, we buy a twice as big system. We spend more money, so we have more concentration on the top. So in some way, those three effects, which look separate, actually tie very neatly together. And I thought that was very, very, very neat when I discovered that. So, of course, the richness of the top 500 comes out of that fundus of 51 lists now. And I just wanted to show 2 or 3 slides about that history. And when we look about over the history of the top 500, one issue is always that we have now a factor of 10 to the 6, a million time increase in performance between the very beginning and the very end of the list. So if you want to aggregate lists in a fair way and not just emphasize the very recent lists, we have to do it in a way which equalizes each contribution of each of the lists. So what we do is basically we normalize it, just like a machine learner would do or a data scientist would do. We normalize each of the lists by the average performance of the list. So all the systems in each list contribute together the same amount of merit to the statistics. And I'm going to show just 2 of the examples for that. So this is not yet done. This is a traditional logarithmic scale performance growth slide, but it shows the life of all the number 1 systems. So if you had a number 1 system, you're going to find the line there, and it shows it should be horizontal if performance is constant, and it should go up if you upgraded your system in the meantime or installed it in pieces. And if you decommission in pieces, it might actually drop off at the end. The length of the bar shows you something about how much cycles over the life of that system contributed. And now I'm going to normalize these curves on the horizontal axis for each data point. So they're going to start turning down towards the right. And I'm also going to aggregate them over the lifetime, so they're going to start going back up. But they should be all next to each other. And what we actually see is it turns out like this. So this is how number 1 system accumulate merit or performance cycles over the lifetime from left to right. So they start out around 25 to 50 times an average system. And if you run it a couple of years, you get something like 300, 400, 500. At which point that system has accumulated as many normalized cycles as a whole list has in 6 months. Okay. The reason that I show this is two things. One, which is a little harder to see, is the entry points actually tend to be higher up towards the right-hand side of the curve. And that lone data point at the very right, by the way, that's the new Summit system, because it was just one entry on the list, so there's no curve there yet. But the main reason that I show this is actually that you see visually a very nice bounding box which goes upwards. And the whole statistics is created, the whole measure is created in a way, if the market doesn't change, if conditions doesn't change, you should have a bounding box which is horizontal. So what this upward curve shows is, again, two effects. We buy bigger systems than we used to do in the past, and we operate them longer, so there is more of a chance that they accumulate cycles and merits towards the right-hand side. So this is a nice illustration of the effects I just showed, and we have seen that very, very dramatically on the right-hand side. Looking back over 25 years, the other big question often is, what are actually the important sites? And that's the other statistics I wanted to show, which is based on these normalized cycles over 25 years. And here I did the number 11. When I did the slide first, my institution where I worked, NERSCAL BNL, was number 11, so that's why I picked 11, and I stuck with that. There is another reason that I picked 11. If you look over the names, you're going to find a lot of names which end in NL, like the first 4 and the last 2. Those are all the national labs in the US. They are all funded from mainly funded from the same funding agency, the Department of Energy in the US, which is a big research organization. And it really shows what a dedicated research agenda and research funding agency can do over 25 years range if they really stick to their guns and consistently fund high-performance computing at a high level. So that is the 6 national labs. The first one in this list is actually Lawrence Livermore National Labs, who today received the award for number 3. They are number 1 here because they have a much deeper history, a much longer history for big machines in HPC. That's why they are up with a very comfortable lead up front, up on top, while the number 1 system is installed at the number 3 site, ORNL, which has a shorter history, so it didn't have as a site as much chance yet to accumulate merit, but it's certainly moving up. SNL is Sandia National Labs, and Argonne National Labs is the one at the end, in case you don't know the acronyms. So that's half of that list is basically national labs in the US. There is 2 other groups of labs in there. For instance, NSCC Guangzhou, that's the Taihu Light installation, and Jamstack, which was I think the K computer or the Earth simulator, one of those. So there are a couple of sites which had the number 1 once in a while, and they had very exceptional machines. That's why they show up here. But even more important to me, there are 2 sites in there at number 7 and number 8, NASA Ames and the German Research Center in Jülich, which you might not have expected to be there because they never ever actually had a number 1 system in the top 500. So to be a very important site in HPC does not require you to have a number 1 system in the top 500, but it requires that you have a funding agency which consistently supports you for 25 years and you buy consistently large systems. That's what happened with those 2 systems, the number 7 and the number 8 system. So there are different ways to contribute to HPC and HPC computing, and that's a very nice thing to see actually in the statistics. The one site I actually excluded from this top 11 because it's very hard to track. It's just labeled government. There is probably other sites which would belong here if we really knew the data, but it's very hard to track the details of those sites, so I took that one out. Okay, now coming to the story about China. We have talked about it a couple of times. The Chinese are using more and more systems. That's the red slice. It's going up quite dramatically. And this time we actually have the situation that China has installed more systems in the top 500 than the US. So China is the prime consumer of HPC if you go by number of systems. If you go by performance, due to the very big IBM systems at Oak Ridge and Livermore, the US is actually ahead of China in terms of installed cycles at this point. And I already said China is actually substantially ahead in terms of a number of installed systems, while the other slices in that pie chart are pretty much stable over time. Japan just ahead of the big three economies in Europe. So the news here is really if we take a sort of orthogonal view where I take the manufacturers and I assign a country as a place of origin based on where the headquarters of that manufacturer is. So where are these systems produced? Because traditionally, systems in the top 500 in HPC have always been produced in the US. The US was very dominant at some point with 90% of the systems being produced in the US. And that has rapidly changed the last 2 years. And this time, it's the first time ever that the US is no longer the country which has produced most of the systems in the top 500, but it's actually China. So China has pulled ahead as a producer of HPC systems worldwide. Okay? And there is a little more to that, actually. It's not just that they produce more, because the last couple of times when I was here and talked about it, I pointed out that the Chinese manufacturers sold most or all of their systems in China, and it just so happens that that is not quite true anymore. So if you just go in detail about the manufacturers, Lenovo is actually now the manufacturer which sells the most systems, ahead of HPE, Inspur, then Shugon, then Cray, and then the more specialized manufacturers, including Bull and IBM. Okay? So Lenovo is number one. If you do it by performance, then the two companies we have in the US, which are really specialized on the very high end, which is Cray and IBM at this point, they show up with very big slices. They're on the lead in terms of performance because they sell the very big systems in the US. But otherwise, the order is actually the same. Lenovo is actually third ahead of all the other competitors. And as I said, the new twist here is that Lenovo is the first Chinese company which started to sell systems outside of Japan. So Lenovo has this list, 63 new systems. Out of those 63 systems, new this time, 20 were sold in China, 21 in the US, and 23 in the rest of the world. So they truly sell everywhere at this point. Of course, they have the benefit of the name recognition, which they got from IBM when they took over the IBM business. But these are not IBM systems. These are not systems they sold a couple of years back. These are systems which entered the list the first time. This time around, there are new systems. They are truly Lenovo built. So the market is changing. The conditions in the market is really changing. So that was the twist to the China story, that we see at least one company which is able to sell outside of China. The other Chinese companies are not so much yet, but it's probably a question of time. We're going to have to see. The other aspect I wanted to highlight is accelerators, the other story. So you have seen this slide or versions of this slide before. That just shows the number of systems which actually have some sort of accelerator. And I throw in a little liberally all the Xeon Phi systems which use the Xeon Phi as a main processor here as well. So you see the number of systems goes up, 130. That's about a quarter of the list. It's not too bad. It's nicely going up, but it's certainly not as dominant in number of systems as it is in terms of performance. The important thing to do is here towards the right end to actually ask the question and look as why is the number of systems going up after it had stagnated a couple of years back. And the big new thing there, which I didn't manage to get into this slide, is actually if you look into the new systems, industrial systems in the top 500 in November and June, so the last 1 year, the last 12 months, exactly 25% of those 116 or what systems, industrial systems, 25% actually using GPUs, mostly GPUs as accelerators. That is totally different from before. Before, industry did not buy accelerators, did not buy GPUs. That has changed. Now at least 25% of industrial systems, new industrial systems, use accelerators. So that accelerators are getting adopted in the industry. I tried to filter out those systems and look in a little more detail what they actually do. And it is by no means that this is only machine learning, which a lot of people would immediately assume. It actually goes across board. There is traditional engineering companies in there. There's different companies in there. with very different application profile. So industry is starting to use GPUs. We have managed to do something to make it easier for them, and they're actually on the bandwagon now. This is how the performance share accelerated systems contribute to the top 500, and the increase towards the right-hand side is not just the very new big systems, because some of those, like Summit, actually replaced a Titan, or is replacing Titan at some point, which is also an accelerated system. It's not just the big accelerated systems on the right-hand side, but it is actually this adoption of accelerators by industry which causes that increase of performance share. And we are close to having half of the performance in the top 500 being contributed by accelerated systems. Not quite there, but almost. Okay, with that, I like to touch the two other topics we have here, Green 500 as well as HPCG. Usually, the Green 500, because it lists technology, is a much more lively than the top 500. That's not the case this time. There is only 3 new systems, and the first one, or the first 2 of those, are actually 2 of the new top 5 systems in the top 500. The Summit as well as the ABCI system in Japan. They show very nice performance efficiency, and the Mare Nostrum system, another IBM Power 9 system, also made the top 10. The other systems are the same. The Shobu System B managed to optimize power consumption as well as Limpec performance more, so their value got up. Over time, what that means is we see on all the levels in the list, we see a nice increase of average power efficiency. That's something very nice to notice. And of course, the important thing is this is driven by stages of technology, and we see that the peak, the max efficiency in the top 500, in the Green 500, as you see it, has gone up quite nicely and quite dramatically. The top 500 is still, the average is lagging behind, because some of the technologies which are employed in these very highly efficient systems haven't made it into the broader market yet. But hopefully that's only going to be a question of time. So with that, the last slide before I summarize is the HPCG, the top 10 in the HPCG list. It's not HPCG 500. We have 61 systems which are on that list. And the first 2 entry points there are the 2 new IBM systems at Oak Ridge and at Lawrence Livermore. They are the first systems ever to actually exceed the petaflop mark on the HPCG benchmark. So in that sense, if you believe in that concept of the bookends between HPL and HPCG, we can proudly proclaim that finally all applications can run at petaflops, and if you can't, that must be your fault or something. Of course, I was going to say it's going to be it's the age of petaflops for everybody, but I don't think anybody has a credit card big enough to order one of those and take it home. Other than that, not that much new in the HPCG top 10. I just want to point out it's a very nice mix of architectures in there. The number 3 system, K-Computer, is a very traditional MPP. We have accelerated systems in there, like the first 2. We have a massive, many core architectures in there, which use Xeon Phi as a main processor or the Taiyu Lite system. So to achieve a decent HPCG number, you don't have to have a specific architecture. You can do that with different architectures. And if you look at towards the right, there are 2 columns which say the percentage of HPCG over HPL and over our peak. If you look at that number, if we go into detail and analyze that, we actually see that HPCG performance is very highly correlated with main memory bandwidth. It's something which we wanted to have, and now we actually have the data to show that. And if you want to have higher efficiencies on HPCG, you're going to have to go to much more traditional architectures which can provide that. Okay, that's basically what I wanted to say. This is a summary of the points I already made, and I think I exceeded my time, so I'm going to stop here. Thank you.
Thank you, Eric. So we conclude the top 500 session with a short panel discussion, and I was told that chairs will materialize on stage by the wave of a wand. They're not. Oh, here they are. Okay, perfect. So while the chairs are being brought in, I would like to introduce my fellow panelists who will join me here. Yutong Lu from China. She has been very notable in the top 500 list and in the HPC community. Please join me. In the HPC community for being behind the Tianhe 2 and Tianhe 2A design, and also was responsible for developing the recent upgrade. Steve Conway, who is now with Hyperion and has been in the industry watching and observing and writing what's going on for decades, and certainly a perfect observer of the top 500 list. Thomas Schultes, who is the director of the Swiss National Supercomputing Center, CSCS. And lastly, Steve Scott from Cray. Oh, he is here, okay, who just recognized that he's actually in the audience. But thank you for joining us. Okay, say welcome to my panelists. So I don't want to make this particularly sort of high intensity and ask a couple of questions, and the panelists know the questions that I wanted to ask. And the first question is sort of hopefully an easy one, and this is, I would like to ask each one of you, what is the most significant contribution that you think the top 500 has made to the HPC world? And maybe we'll start with Yutong at the far left from my side.
When I heard about that question, there were two keywords lighting in my mind. One is, I think it's a propagation, and another is the promotion. I think the top 500 list let the public know and understand what HPC is and what HPC could use to do. And also let the medium to help us to propagate HPC concept to the broader area. And another thing is, if we look at the top 500 list, it's not only the rank of the supercomputers, it also could show the key technologies, including the CPU architecture and the interconnect network and the I/O system, etc. So it helps us to help the vendor and users to understand the trend of HPC technology development and promote the HPC technologies used to the system and application.
Yeah, I would agree. I think for me, the single biggest thing, and I attended since the beginning, I think, of this thing, is keeping government funders' attention on HPC. I'd say is the biggest thing, that the contribution it's made over time, and I think that really helped get the HPC community through the doldrums, the economic doldrums of the post-Cold War era, when there was a big dip and people worried about the continuation of supercomputing much more easily. And I also think that today the exascale race would be, without the top 500, the exascale race would be 3 or 4 years further in the future.
Thanks, Steve.
I think I switched the mic here. Yeah, I fully agree. The single most contribution is really the attention that Top 500 brings to HPC. HPC is scientific computing, and it's amazing the amount of political attention we see around the world to this problem. I think science can be very happy with this, and from that point of view, I hope the attention will continue in the future.
Thanks. Well, everybody likes a horse race, and so that was on my list as well, the publicity aspect. But I'll say that I think the #1 contribution has just been the historical record. Nobody thinks that LINPACK is the quote unquote right metric to judge the performance of a machine on real workloads, but it's not bad, and I think the genius was in the simplicity of the benchmark, which meant that pretty much everybody could run it. And we've now got this incredible wealth of 25 years worth of historical data about our industry. We can see trends in processors, we can see trends in countries and interconnects and vendors, all these different ways of analyzing the data. And we've seen the three of you give all these talks over the years, and it's just great. There are so many different ways you can parse the data. And so each list gives us about 2 orders of magnitude of the top part of our industry. So you're not just looking at supercomputing and high-end supercomputing, you're kind of looking at the whole HPC industry. And I think that part's been really invaluable.
Okay, so this was the warm-up. I tried all of you to be very generous and say nice things about the top 500. So now let's turn this around and say, what is it that you don't like? What would you change? What would you do different? What should be done? So you all look expectantly. Maybe you, Tong, I'll let you go first. Any recommendations, improvements?
Yeah, I think the performance for the supercomputer will be an internal topic. So because people always ask how faster, they consider and care about how faster the supercomputer could run and how higher the performance it could be reached. But I think the measurement methods could be changed in needed. If you look at the past 20 years or more than 20 years, at that time, the computational power, it's maybe the bottleneck of the whole system application. So the HPL, I think it's a good benchmark at that time, and also in the recent 20 years. But now, we all noted that maybe the data accessing ability become the bottleneck of the system and application. So obviously we need some new benchmarks to measurement that part. So I think that will be something we need to change.
Sure. Thank you. Steve?
Yeah, I mean, the top 500, as Steve was saying, great as a census of developments affecting large supercomputers over time, but it's often been, interpreted, and it was never intended to be a predictor of performance on a broad spectrum of HPC code. So I would have said before I came here today that one thing, and I've said it in the past, one thing that would be valuable is kind of a warning like on a cigarette label that says this could be fatal if you use it as a predictor and so forth. But I was very, very pleased to see the attention paid to HPCG and the Green 500 and the inclusion on those lists. And so my only recommendation would be to give those equal promotional strength.
Thanks.
You want to do that?
Yeah, I think here I don't fully agree or have quite a different opinion. You asked the question a bit different, the relevance today, and the relevance is clearly from a political point of view and funding point of view. From an application performance point of view, the story is very different, and as we all know. And I think we need, and it even comes to the point where top 500 may actually be a distraction if you have certain goals on the application side. And let me give you an example. If you take the systems that were discussed, there is the Taihu Light system in Wuxi and the Pitt-Stein system that I have a lot of authority over. When you look at the flops per second, there is a factor 5 difference. So Pitt-Stein is a factor 5 weaker in performance. When you look at how a benchmark from the weather and climate community performs, there is this baroclinic instability test, then the order is reversed and the performance is about 2 to 3 times faster. So you can have a factor 10 discrepancy. And we've been thinking about this quite a bit, because the question is what you do to change the metric. And it turns out ECMWF, by the way, has a much more interesting data set that goes back to the 70s, looking again at their model performance. And it turns out that floating point operations per second is not a good metric to design system against. It may be good to track, look back retroactively, but not looking into the future. And the conclusion we have, and we've been looking at this in a paper that I heard last night was accepted, is we need a metric that relates to a scientific goal. So simulated years per day for a given size of problem. And the size of problem is very important that this factors in. Remember, in top 500, in HPL, we can tune the size of the problem to maximize this metric of flops. We can do the same for HPCG. It turns out from an engineering point of view, this is not good. You're not going to change your target. If you're paid to do something, you're not going to change your target just to maximize some number, okay? That's a really bad idea. And the third point, so we need to set goals. Like in weather and climate, I think they have very clear goals that everybody can relate to. And I wish that the scientific community could come together behind a few goals rather than everybody wanting their own code to be somehow the metric. And the second one is not just some performance metric, but the size of the problem needs to be set and can be varied over time. But we need to compare apples to apples and not apples to oranges. And the third point, and that is really missing in top 500, is the algorithmic or the method side. Methods, changing algorithms in the computation, in the history of computing is just as important as changing architectures. And we somehow need to allow that to be factored in. So those are my 3 recommendations that we look at when we go forward.
Thank you, Thomas. Steve.
Yeah, I mean, from a scientific perspective, I couldn't agree with you more. From a practical perspective, I can't agree with you at all. and that is, I would love to see simulated years per day as a much more interesting and useful metric, but there's no way that you could do that, right? And you can't really change the metric that the list uses because then it sort of invalidates that historical record aspect. So we have to count on people that are actually doing procurements and fielding these big systems to be sophisticated, people that understand what's really important and that LINPACK is not that thing. And I absolutely think that the top 500, despite all the good that it's done, has caused some bad behavior, right? People have made decisions to get a higher ranking on that list. And then there have been other people that said, I'm going to buy a supercomputer and I'm not even going to put it on the list because I don't endorse the metric. I think the reality is that you're not going to be able to change the top 500 benchmark. I like the idea of augmenting it with some things, and there have been some attempts with HPCG and the HPCC benchmarks and that sort of thing. So we could augment it. I don't think we can change it. I think that it is becoming more and more, the HPL performance is becoming more and more disjointed from real application performance as we move forward, and memory bandwidth and interconnect and other things matter a lot more, and architectural aspects matter. As we get closer to the end of the CMOS era, and we may change the way we do computing or go to completely different architectures, it may become even more stressed to the point where we kind of have to do something. But in the meantime, I'm not sure that there's a whole lot we can do other than sort of continue on the current path.
Yeah, I was going to come to your point, Steve, in a minute on the maybe have to change it because of the trends in computing, but I wanted to sort of ask a more personal question, and this is sort of, you can volunteer here to speak up. Do you have any interesting stories of your personal career, how you were intertwined with a top 500? Politicians calling you in an office and saying, how come you're not number 1, or things like that? It has happened, I was told.
I myself have stepped on the top 500 world stage for more than for 10 times, exactly 6 times for number 1 and then 4 times for number 2. Yeah, it's. I think I appreciate about that this experience. I think it's. Yeah, it still impact for some of my career or my personal development. I think it's an important thing is the number 1 system leading me to connect with the international HPC community. And so I and my team, the Tianhe team, and the Chinese scholars could have a chance to exchange ideas and technologies with the people all over the world and broaden my view. Another thing I think also leading me change a little bit of my personal research priority and direction. What can I say that it's come from transfer from the system-centric to the application-centric? Because, you know, before the Tianhe 1 and Tianhe 2 become the number 1, I have involved in the system design work for the Chinese supercomputer for more than 15 years. At that time, I'm focused on to design and implement the high-performance system software, the communication library, the MPI, the job scheduler, and the file system, etc. At that time, I also help people to optimize the applications. But I do that, I try to demonstrate how powerful our system is. And after we become the number 1 and got more attention about the system, and the people also consider and care about how the Tianhe 2 system is used. What can the support the scientists or the society to do the broader application? So it make me change my view to think about that, how if we have some application requirements come from not only the conventional HPC era, also come from life science, the smart city, the new emerging applications. So I try to establish some new domain-specific application platform to support our end users, not just to think about our system, but think about our user application. Yeah.
Thank you.
Yeah,
so I gotta ask you to be very short, 30 seconds or 45 seconds, let's say. Everybody.
It'll be short.
It'll be short.
Just as a follow-on to what we were talking about before, I wanted to say that even as the top 500 kind of keeps the government coffers pouring money into this industry, and important for that reason, I think it's also a very good development that a lot of the big initiatives like ECP in the US, Euro HPC, and initiatives in Asia too are making the internal metric performance gains on their own applications.
Very good point. Yes.
Well, I've been thinking it's a hard question to answer. The agency that funds us, the ETH board, is putting really all the relevance on the internal metric on certain applications. And so in that sense, the top 500 can become a bit annoying because we have a clear goal that we have to deliver, say, systems for Meteor Swiss with set performance. And then people ask me, why is this not on top 500? Or what is the top 500 performance going to be of your next system? And this is what I mean by a distraction. Yes. And it can be a real problem. So I'm sorry I can't give you a more positive answer.
Well understood. In the good and the bad way.
And I'm kind of in the same camp as Thomas. I mean, we try to spend all of our time focusing on sustained application performance and working with people like Thomas to make machines do useful things. And the top 500 is just, it's always there kind of in the background about, where will you be in the rankings. And it can be fun when you happen to have a machine that shows up and you get to, but the reality is that we mostly concentrate on applications.
Okay.
It has been kind of nice because my career kind of started with the T3E back in that we started working on in 92, 93, right at the beginning of the list. So it's been kind of documenting that period of time. So it's been kind of fun for me personally to see that progress.
Okay, so I promised two things, finishing quickly, but also, if we have time, to ask you a real challenging question. So I want you, if you have the answer to the question, just say the answer and maybe 2 words about why you came up with this answer, but no long explanation. So in 25 years, in another 25 years, which is, I believe, 2043 or maybe 2042 if you go back, what do you think the #1 system of the top 500 list will perform?
2 words. One's Zota, I think Zota flops, and another is maybe another quantum computing system.
Okay.
Single-digit zettaflop.
I think it will not exist anymore. In its
I was
current
hoping
form.
somebody would say that.
In its current form, and we see some of this already today. Many applications run much better at lower precision, and didn't UJAC show that even the dense linear algebra problem of HPL can be solved more efficiently in mixed precision with tensor flops? So either we change the rules and then your historic record goes out of the window, or it just doesn't pay anymore to worry about top 500.
Yeah, I don't know if we're going to get a CMOS replacement or not. If we don't, I think we'll be at kind of 10 exaflops, and if we do, I'll say 10 zettaflops. Just, not quite the same 6 orders of magnitude we've had in the past. But yeah, 25 years from now, we could finally maybe have a quantum computer that was useful as well. So, it could be a different landscape.
And who will be at ISC 42? I'll plan. No? Okay, well, I think the comments were really insightful, both looking back and looking in the future, and hopefully give you a lot of stimulation to have continued conversation amongst yourself and with the panelists during lunch. Thank you for joining us.